Episode 20. The title of the course is Advanced Materials Science, Unit 5. In this episode 20, we will continue the applications of ferrites. Now we'll see on gyrators. It is a two-port unit which transmits power freely in both directions but has differentially phase shift of pi radians between the two directions. Let us see a gyrator function based on a 90-degree Faraday rotation by ferrite rod. Faraday rotation refers to the rotation of the linear polarized electric vector by the ferric rod. The ferric rod is located centrally in a section of circular waveguide by means of a polyfoam support, whose permittivity is slightly greater than that of air. The ends of the ferrite rod are tapered to prevent unduly large impedance mismatch at the transition from empty waveguide to ferrite loaded waveguide. Transitions are provided from the circular to the rectangular waveguide, and a section of the latter incorporate 90-degree twist. A solenoid surrounding the ferrite section applies an axial steady magnetic field HO of such magnitude that the Faraday rotation through this section is 90 degree. A wave traveling from A to B has its electric vector tuned through 90 degree clockwise about its direction of propagation. In passing through the twist, and a further clockwise rotation of 90 degree is brought about by the ferrite. The total rotation is referred 180 degree or pi clockwise rotation about its direction of propagation in the ferrite, and a clockwise rotation of 90 degree in the twist. Thus the initial direction of its electrical vector consequently restored. Thus the different phase shift of pi radian is obtained and the unit functions as a gyrator. Next we will see about isolator. Isolator is two-port element displaying differential attenuation. A thicker ferrite slab of reduced height is placed in the waveguide and magnetic bias field is applied externally. The ferrite slab is cemented along its faces of contact with one of the broad walls of the waveguide. The reduction in height of ferrite slab reduces dielectric losses in ferrite and enhances the ratio of forward to reverse loss result. The large area of contact between the ferrite and metal waveguide increases the cooling, which is very important in higher power applications. The value of the ferrite slab permeability depends upon the sense of circular polarization of the wave. It has high value of 1 sense of circular polarization and very small value of other sense of circular polarization. Wave traveling in one direction in the ferrite slab have 1 sense of the circular polarization, while those in the opposite direction have the other sense of circular polarization. Hence, the wave traveling through the guide in the ferrite slab in one direction are strongly attenuated, while the waves traveling through the guide in opposite direction are passed through almost loosely. In simple isolated service, attenuation ratio of 40 decibel in one direction to 0.5 or 1 decibel in the opposite direction can be obtained. Generally, over fractional bandwidths of 10 or 20%, this device can also made into short modulator or switch by switching the amplitude or direction of the biasing magnetic field respectively. Then we move on to circulator. It is the multi-port non-reciprocal device providing sequential transmission of power between ports. Ferrites in waveguide configurations can also be used as field dependent and therefore magnetically controllable phase shifted or a phase shifters which shift the phase of electromagnetic waves of different polarization by different amount. This principle is used in circulator. Let us see 3-port ferrite circulator. There is a single cylinder of ferrite, singles of into A come out of B, signals into B come out of C, those into C come out of A. This is possible if the phase shift between ports is 60 degree in one direction but 120 degree in the opposite direction. The symmetry of the device divides the input at any port into two paths. Recombining at each of the two other ports, the two halves of signals are 180 degree out of phase at one but exactly in phase at the other. Using circulators we can get gyrator or isolator function. Thus a 6-port circulator can serve as gyrator and 3-port circulator can serve as an isolator. Based on nonlinear tensor permeability property, ferrites can also be used in device for power limiting and harmonic generation. A ferromagnetic amplifier of microwave signals using ferrites can be designed utilizing spin of large amplitude as the coupling element. The use of ferrite in this paramagnetic amplifier provides very low noise figures. Ferrites are also used in digital computers and data processing circuits. Normally here ferrites with rectangular hysteresis loops are used as magnetic storage element. Then we move on to bistable elements. Ferrite core can be used as bistable element since after passage of saturation magnetizing current pulse, the remagnet flux will be either positive of pi or negative of pi r depending on the direction of the current pulse. In the absence of demagnetizing influences, the core will hold this remanent flux identically without further power consumption. It can therefore function as a storage for information in the binary code such that minus pi r and plus pi r may represent 0 and 1 respectively. To read the stored information, a negative current pulse of the same value of original current pulse for stored information may be passed through the primary or a further readout winding. Since eddy current are almost zero even under large and rapid flux, in ferrites these materials appear to be an obvious choice for switching core in computer provided that they can be made to show the regularity in their hysteresis loop. Then we move on to magnetic shift register. The function of magnetic shift register or delay line is to accept and store information in binary code. The rectangular loop ferrite cores with low value of the switching coefficient and threshold field are used. We can construct magnetic shift register requiring 2 cores per store digit or only 1 core per digit using rectifier circuit. Shift registers provide versatility facility for data storage and handling in computers. These can be used as frequency divider. Large-scale ready access storage facilities can be provided conveniently by magnetic storage. Then we move on to magnetic bubbles. Magnetic bubbles are almost soft magnetic material with magnetic domains of a few μm in a diameter embedded in a matrix of a different spin orientation. These bubbles are the electronic analog of the magnetic disk memories used in computers. The magnetic tape in the disk memory is moved mechanically, whereas the bubble in a bubble memory device are moved electrically at very high speed. So the readout time or sorting time is greatly reduced in bubble memory device. The above applications are all based on the property of soft ferrites. We have some hard ferrites which are used to make permanent magnets. Barium ferrite, that means BaO6Fe2O3, is one of the hard ferrites which is produced by sintering of mixture of barium and ferric oxide. It is entirely different from the above said ferrites both in crystal structure and magnetic properties. It has enormous high and can be used to produce large magnetic field flux and operate efficiently without external soft ion circuit, unlike alnico alloy. Garnets are almost ferrimagnetic material like ferrites with the general formula M3Fe5O12, where M is trivalent metal ion and Fe is trivalent ferric ion. These are soft magnetic material with small eddy current losses due to their high resistivities and small hysteresis losses at microwave frequency. These have narrow resonance line width and are widely used as microwave isolators in gigahertz range. The yttrium ion garnets, that means YIG or Y3Fe5O12, belongs to the rare earth ion garnet group and has very low magnetic losses than those of ferrites due to ordered arrangement of ionic in the lattice. The oxygen lattice on which the structure is built is again of tube close packed form with a unit cell containing 8 molecules of Y3Fe5O12. The large yttrium ion pushes back oxygen ion to form the site neighbored by 8 oxygen atoms. All sizable exciting voids are then occupied by yttrium or ions, and there is no randomness in the ion distribution. Then we move on to next topic, different types of hard magnetic material. Energy product of a magnetic material. Hard magnetic materials with large energy product BH are used to produce permanent magnets. The energy product gives the energy required to demagnetize a permanent magnet. Here B is the residual magnetic induction and H is the corrosive field strength. High carbon steel, low alloy tungsten, chromium steel and cobalt steel in the condition are used to produce permanent magnets in this material. The enormous value of mechanical hardness improves the resistance to domain wall motion. Example, carbon steel 1% Mn, 0.9% C, 98.1% Fe. Chrome steel 3.5% Cr, 0.9% C, 0.5% Mn and 95.1% Fe. Then cobalt steel 20% Co, 0.7% C, 7% W, 3% Cr and 69.3% Fe. Among the metallic alloys, alnico alloy are important. These are carbon-free non-machinable alloy. Magnetic properties of this alloy are stables with time and temperature. These are difficult to cast and hence these are made with powder metallurgical technique followed by edge hardening in magnetic field. Heat treatment of alnico alloy in a magnetic field increases the magnetostatic energy considerably. Among the common hard magnetic material, only the alnico alloy have higher energy product value. Alnico 2, 10% of Al plus 18% of Ni plus 12% of CO plus 6% of Cu plus 54% of Fe, and alnico 5 is 8% of Al, 14% of Ni plus 24% of CO plus 3% of Cu plus 51% of Fe are important types. The high percentage of cobalt 50 to 40% promotes residual magnetism and corrosive magnetic force in iron. Thus alnico 5 has more energy product than alnico 2. Very small powerful magnet can be produced from these alloys. Further, permanent magnets with very large energy product are produced from cobalt alloy with rare earth elements. Cuneifies, that means copper nickel iron. Cunico, copper nickel cobalt. Silmanal, Ag, M and Al are important carbon free measurable magnet alloys. Magnetic property are improved by precipitation, hardening and serve cold working. Permanent magnet with higher magnetostatic energy are made by pure iron with single domain or iron cobalt powders compact on a magnetic field. These are pressed powder magnet, ESD, elongated single domain. Magnets are also made by the above process using fine particles of iron. Metal oxide magnets are produced from metal oxide powder which are pressed into the desired shape, sintered and finally heat treated in a field. These have higher chemical stability. Example, iron cobalt oxide magnet, 30% of Fe2O3 plus 44% of Fe3O4 plus 26% of CO2O3. There are some non-metallic oxide magnetic such as barium ferrite, already discussed in ferrite topic on last episode, which have high energy product than alnico alloy. Very important properties of FeSi alloy. Maximum relative permeability is 7000. Resistivity is 6 times that of pure iron. Application is cores of power transformers. Next, permoalloy. Maximum relative permeability is 25,000. Higher hardness. The application of permoalloy is cores of audio and video transformers and communication equipments. Next, supermalloy. The property is maximum relative permeability is 8,000,000. Very high hardness. Then next one is mu metal. Maximum relative permittivity is 1,000,000. High stable magnetic property even at very high frequency. High corrosion resistance. The application of this material is cores of audio and radio transformers. The next material is NiZn ferrite. The important property is very high resistivity, narrow hysteresis loop, maximum relative permeability is 5000. The application of the NiZn ferrite is cores of audio and TV transformers. Next one is MnZn ferrites. That means 80% of MnO plus 20% of ZnO Fe2O3. The important properties is maximum relative permittivity is 2500. Very high dielectric constant. The application of the MnZn ferrite is microwave isolators and gyrators. Next alloy is MgMn ferrites. That means 50% of MgO plus 50% of MnO Fe2O3. The important properties of MgMn ferrite is rectangular hysteresis, very high resistivity and low eddy current. The application of the MgMn ferrite is memory core in computers. Then we move on to YIG alloy. That means Y3Fe5O12. The property of YIG alloy is low eddy current losses, very high resistivity, very high dielectric constant. The application of the YIG alloy is microwave equipment as non-reciprocal devices. Then we move on to another alloy, tungsten steel. That means 6% W, 0.7% C, 0.3% Mn, 93% Fe. The important properties of tungsten steel is higher strength and higher hardness than carbon steel. The application of the tungsten steel is for making permanent magnets. Next one alloy is high chrome steel. That means 3% Cr, 1% C, 0.4% Mn, 95.1% Fe. The important property of high chrome steel is higher hardness, higher corrosion resistance. The application of the high chrome steel is magnets with stable energy product for making permanent magnets. Cobalt steel, KS magnet steel. That means 36% CO, 7% W, 3.5% Cr, 0.9% C, 56.3% Fe. The cobalt steel, that means KS magnet steel, property is high corrosivity, high magnetic strength. The application is for making permanent magnets. Aluminum nickel cobalt alloy. That means 12% cobalt, 17% nickel, 10% aluminum, 6% copper, 55% iron. The main aluminum nickel cobalt alloy property are high magnetic strength, high mechanical strength, produced by powder metallurgy. Alnico 5 is more powerful than Alnico 2 due to higher percent of cobalt. The main application of aluminum nickel cobalt alloy is for making powerful permanent small magnets. Then move on to cunifies. 6% copper, 36% nickel, 58% Fe. Cunifies having most important properties that are carbon free machinable alloy. Magnetic properties are improved by hardening. Cunifies having a important application for making large permanent magnet. Cunico 6% copper, 40% nickel, 54% cobalt. The important property is carbon free machinable alloy for making large permanent magnet. Barium ferrite BaO 6Fe2O3. The important properties of barium ferrite is highly corrosivity, high stable magnetic property, Barium ferrite alloy having a very good application for making powerful magnets. The important points of this unit 5. Magnetism arises from the orbital and spinning motion of revolving electron in atoms. Dia, para and ferromagnetic material are the important magnetic material. Diamagnetic material have negative susceptibility. Paramagnet and ferromagnetic material have positive susceptibility. Enormous magnetization in ferromagnetic material. Even the weak applied magnetic field is due to spontaneous magnetization which arises from the favorable exchange interaction between adjacent spins. The hysteresis loss will be small for soft magnetic material and it will be large for hard magnetic material. The area of BH loop represents the energy loss per meter cube of the specimen during one cycle of magnetization. Finally, we will see about what are the essential difference between hard and soft magnetic material. Hard magnetic materials are a large area hysteresis loop. Soft magnetic materials are smaller area hysteresis loop. Hard magnetic materials has highly corrosivity and highly tendentivity. Soft magnetic material has less corrosivity and less retentivity. Hard magnetic material has irreversible domain wall moment. Soft magnetic material has reversible domain wall moment. Hard magnetic material has lesser permeability. Soft magnetic material has large permeability. Hard magnetic material is used for making permanent magnets. Soft magnetic material is used for making electromagnet. Since soft magnetic material can be easily magnetized and demagnetized, these are used to make electromagnets used in currents. Due to their low hysteresis loss, they are also used in transformer core material. Transformer core material should have highly resistivity to reduce eddy current losses and magnetically soften and reduce hysteresis losses. Magnetic material whose length along the axis magnetization may change when it is placed parallel to magnetic field are called magnetostriction material. These are used to produce ultrasonic waves and design mechanical filters used in the single side band transmission of ratio waves. The magnetic moment originates from the orbital motion and spin motion of electron in atom, particularly ferromagnetism, is mainly due to spin-spin interaction of unpaired electron in ferromagnetic atoms. Ferrites are soft magnetic materials having the general formula XFe2O4, where X is divalent metal like Mn, Mg, Ni, Fe, etc. These are ferrimagnetic material having opposite and different magnitude spin in the adjacent ion in the lattice. These are have high resistivity and low hysteresis loss at radio frequencies, and hence these are used as transformers core materials at those frequencies. Ferrex cubes are the soft magnetic materials having narrow rectangular hysteresis loops. These are used in computer memories. Garnets and soft magnetic materials having high resistivity, low hysteresis loss and low current losses. These are used microwave frequencies as an reciprocal microwave device. Example: yttrium ion garnets. ESD magnets are elongated single domain magnets. These have very fine particles with large magnetization. These are stable towards their magnetic property and have a single domain structure. Dear student, we are now in the end of Unit 5 and also end of this course. Thank you very much for listening this course. I am sure this is very important and interesting course. Thank you once again.